Hello and welcome you all in our fifth lecture of refrigeration and air conditioning. In the previous lecture, we studied uh, about the various aspects of the psychrometric chart. About also we discussed how we can calculate the various thermodynamic properties of the moisture using the psychrometric chart. Now in the current lecture, that is lecture 5, we will continue from our lecture number 3, where we studied four processes performed by the moist air on the psychrometric chart. The four processes that we studied were sensible heating, sensible cooling, humidification and dehumidification. They were the basic processes that can be performed by the moist air on the psychrometric chart. But we all know that the humidification and dehumidification cannot take place alone. They will always be coupled with some kind of heating or cooling. Therefore such type of combinations we will be studying in this lecture. The process that we are going to study here in the lecture, the first process is adiabatic or chemical humidification. In this process, the adiabatic and chemical humidification, one thing that has to be kept in mind, that during this process enthalpy of the moisture will remain constant. Enthalpy will remain constant. Now we will try to see this process on the psychrometric chart. Let's draw a psychrometric chart. This is a simple psychrometric chart where vertical axis is specific humidity, horizontal axis is temperature, and this is relative humidity is equals to 100%. That is saturation curve. Now the process in such a the process is being taken place in such a way that the enthalpy remaining constant and the cooling and humidification is taking place. The process shown here is from state 1 to state 2, and during this process the cooling of the moisture is taking place as well as the humidification is happening. Let us draw the vertical lines from state 1 and state 2 on the temperature axis. By drawing the vertical line, we can get the temperature T1 and T2 at the horizontal axis. T1 and T2 are the drivable temperature of the moisture initially and finally. Therefore we can see the temperature is reducing, drivable temperature is decreasing. Now talking about the specific humidity, to calculate the specific humidity we need to draw horizontal line from the state to up to the vertical axis. Therefore the state 1, the corresponding to the state 1, the specific humidity is omega 1, and corresponding to state 2, specific humidity is omega 2. We can see that specific humidity is also increasing. Therefore specific humidity will be increasing. Talking about the enthalpy, since we know that the adiabatic and or chemical humidification is a process in which the enthalpy remaining constant, therefore enthalpy will remain constant. Talking about the wet bulb temperature, we all know that the wet bulb temperature is obtained by joining wet bulb temperature at any state, either state 1 or state 2, can be obtained by drawing a line horizontal to the constant enthalpy line up to the saturation curve. If we draw a line constant enthalpy line up to saturation curve, then for state 1 as well as for the state 2, the line will be same. Therefore the wet bulb temperature will be same for state 1 and state 2. Hence the wet bulb temperature will remain constant. Talking about the dew point temperature, we all know that the dew point temperature is obtained by drawing a horizontal line in such a way that finally it joins with the saturation curve. Therefore, if we draw a such if we draw a horizontal line in state 1 and state 2, at a state, this is state 1 and this is state 2, then the corresponding temperature, the temperature corresponding to the line, to the point when the constant specific humidity line matches with the saturation curve, and this temperature will be dew point temperature at state 1, and the temperature corresponding to this point when the horizontal line from state 2 touches the 100% relative humidity curve, that is saturation curve, then the temperature corresponding to that point will be the dew point temperature at state 2. Therefore we can see that the dew point temperature is increasing. So these are the various effects of the thermodynamic on the thermodynamic properties of the moisture because of adiabatic or chemical humidification. Similar to the adiabatic or chemical humidification, there is one more process, that is adiabatic or chemical dehumidification. Adiabatic or chemical dehumidification is a process is a process just reversed, which is just reversed to the uh, adiabatic or chemical humidification. If we want to show the process on the psychrometric chart, then the process which is just reversed the adiabatic humidification. Adiabatic humidification was from here to here, whereas the adiabatic dehumidification is a process from 1 to 2, while the dehumidification is a process from 1 to 2, while the adiabatic humidification was a process from 2 to 1. In this process, also enthalpy of the moisture remains constant. That is the definition of adiabatic or chemical humidification, that comes along with the definition. If we talk about the dry temperature is increasing. If we talk about the specific humidity, is decreasing. If we talk about the relative humidity, is also decreasing. If we talk about the enthalpy remaining constant. Wet bulb temperature will also remain constant. If we talk about the dew point temperature, will also reduce. All the effects on all the effects on thermodynamic properties due to adiabatic dehumidification is just opposite to the effects that were taking place because of the adiabatic humidification. Now the next process is adiabatic saturation. Adiabatic saturation is such a process in which adiabatic humidification is taking place in such a way that the final state of the moisture is saturated, that the state 2 is saturated. This process is known as adiabatic saturation, that is, it is adiabatic humidification itself, in which the enthalpy remains constant but final state of the moisture is saturated. This is adiabatic humidification, along with final state being kept at saturated condition. Therefore the above process is known as adiabatic saturation. All the effects on the thermodynamic properties because of adiabatic saturation will be just similar to the effects on thermodynamic properties due to adiabatic humidification. Moving on to the next topic, cooling and dehumidification. This process is very important from the point of view of summer air conditioning because all the summer air conditioners perform the cooling and dehumidification process on the moisture. What happens in the cooling and dehumidification process is, let's see on the psychrometric chart. Since the name of the topic has been made from the two processes, sensible cooling and this another process is dehumidification. There will be sensible cooling of the moisture and also there will be dehumidification. So the process will be something like this from state 1 to state 2. The process shown here is cooling and dehumidification. If we talk about the initial and final dry bulk temperature, then we need to draw a vertical line. We need to draw a vertical line from state 1 to state 1 and state 2 up to the temperature axis, and we can see that the initial and final temperature can be calculated from this axis, and initial temperature is greater than the final temperature, hence the temperature is reducing. If we talk about the specific humidity, we need to draw a horizontal line from state 1 and state 2. We can easily understand that the specific humidity is also reducing. This is the process, and the specific humidity is also this process is actually actually taken place in the uh, summer air conditioning systems. If we extrapolate the state the 1 to 2 process and touches, and this line, when this line touches the saturation curve, this point is known as apparatus dew point. The temperature corresponding to the apparatus dew point will be called as ADP, and this is nothing but the temperature of the cooling coil. The point of intersection of the saturation curve and the cooling and dehumidification line give the apparatus dew point. Point of intersection of saturation curve and cooling and dehumidification line gives the apparatus dew point temperature. Apparatus dew point. Yes. Temperature corresponding to this point is called apparatus dew point temperature or temperature of cooling coil. we need to understand that whenever there is cooling of the moist air, that the process, if we talk about the process cooling and dehumidification, the our process will be carried out by the air conditioning system in a certain space where there will be a cooling coil, and the air will enter at temperature T1 and specific humidity omega 1, and will come out as T2 and specific humidity omega 2. This air will be cooled down by the cooling coil. Then the temperature of this cooling coil should be very lesser than the initial and final temperature of the uh, moving air, that is the moist air. So this temperature of the cooling coil is adiabatic, apparatus dew point temperature. Apparatus dew point temperature will always be lesser than the dew point temperature of the moist air. This is the important point we need to know. Apparatus dew point temperature or temperature of cooling coil will always be lesser than the dew point temperature of moist air. So this brings us the end of this lecture, in which we have studied the few more processes that are performed by the moist air. In the coming lecture, we will be studying about two important things, that the efficiency of the cooling coil and bypass factor. Thank you.